You're listening to Who Said, a Cardiology Board Review series. No fluff, just facts.
This episode is about calculating pulmonary artery pressures. There are several ways of calculating pulmonary artery pressures. We'll go over systolic PA pressure, diastolic PA pressure, mean PA pressure, and the methods to calculate each one. Although this is a short episode, I think it is an important episode for understanding some fundamental concepts both for the echo board exam as well as the general cardiology board exam and in daily clinical use. Let's start with systolic PA pressure. The systolic PA pressure is often approximated by the right ventricular systolic pressure, RVSP. The tricuspid regurgitant velocity, VTR, is a reflection of the pressure difference, delta P, between the right ventricle and right atrium. The delta P of the RV minus RA is simply 4 times the square of the V max TR. Since the pressure difference between the right ventricle, which has a higher pressure, and the right atrium, which has a lower pressure, is known based on the VTR, the tricuspid velocity, all we have to do is add the pressure difference to the existing RA pressure to obtain the RV systolic pressure, RVSP. So RVSP equals RA pressure plus delta P of the RV RA difference. So this is a very basic and common equation that is used in all echo reports when people estimate the RVSP by adding this delta P RVRA to the estimated RA pressure. As long as there's no pulmonic stenosis, which is rare in adults anyway, unless you have congenital heart disease, the RV systolic pressure can be treated as the same as the pulmonary artery systolic pressure, PASP. So, PASP is approximated by RVSP, which is RA pressure plus 4 times the square of V max tricuspid. So, for example, if a patient had a right atrial pressure of 10 millimeters of mercury and a TR velocity of 2.7 meters per second, the PA systolic pressure is approximated by RV systolic pressure, which is 10 millimeters of mercury of RA pressure plus 4 times the square of 2.7 meters per second, which gives you 39 millimeters of mercury as the estimated RVSP or PASP. If pulmonic stenosis is present, then you're going to have to remember to subtract the peak pulmonic stenosis gradient, delta P pulmonic stenosis. And all that is just one additional step, one additional term. So then your PASP equation becomes PASP equals RA pressure plus 4 times the square of V max tricuspid minus delta P max pulmonic stenosis. Next, let's talk about diastolic PA pressure, which is approximated by the right ventricular diastolic pressure. The same way we use tricuspid regurgitant velocity to estimate RV systolic pressure, we can use the pulmonic regurgitant velocity at the end of the PR envelope, the end of the pulmonic regurgitation envelope on Doppler, to estimate the RV diastolic pressure by the simplified Bernoulli equation. So PA diastolic pressure equals the RA pressure plus 4 times the square of V end pulmonic regurgitation envelope, VNPR. Now, how about mean PA pressure? There are actually 5 ways to obtain a mean PA pressure on echo. First, to obtain mean PA pressure, you can trace the TR velocity profile to obtain the VTI, the velocity time integral, and the subsequent mean gradient. Once you obtain the mean gradient, you can add it to the RA pressure to get the mean PA pressure. So MPAP equals RA pressure plus mean delta P of the RVRA. For example, if on CW Doppler of tricuspid regurgitation, the tip of the down hump corresponds to a velocity of negative 4.4 meters per second, then the RV systolic pressure is 4 times the square of 4.4 plus RA pressure. The mean RV-RA gradient should be given to you on the screen once you trace the VTI. But if it is not given to you, you can approximate it by using 2.4 instead of 4 in your coefficient. So the mean delta P RVRA is 2.4 times the square of V max tricuspid regurgitation equals 2.4 times the square of 0.4 equals 46 millimeters of mercury. if the mean RV-RA gradient is given to us, for example, 43 millimeters of mercury, then MPAP is just 43 plus the RA pressure. The second way to obtain the MPAP is by applying the simplified Bernoulli equation to the peak pulmonary regurgitation velocity, VPR, at the peak of the PR envelope and adding that to the RA pressure. Remember that when we use the NPR envelope velocity to calculate diastolic pulmonary artery pressure, if we use the peak PR envelope velocity, we can calculate the mean pulmonary artery pressure. MPAP equals RA pressure plus 4 times the square of Vmax pulmonary regurgitation. For example, if the CW Doppler of PR shows that the tip of the up hump corresponds to a velocity of 3.2 meters per second, and at the end of the envelope it corresponds to a velocity of 2.0 meters per second, then MPAP equals 4 times the square of 3.2 plus RA pressure. DPAP equals 4 times the square of 2.0 equal plus RA. Third, MPAP can be estimated from the RVSP using Chemla's formula in CHEST 2004. MPAP equals 0.61 times RV systolic pressure plus 2. Fourth, you can measure the pulmonary artery acceleration time, AT, and just do MPAP equals 79 minus 0.45 times acceleration time. If the acceleration time is 120 milliseconds or less, then you should use the equation MPAP equals 90 minus 0.62 times acceleration time instead. Fifth, if you have already obtained the PA diastolic pressure and PA systolic pressure obtained above, then you can simply do MPAP equals SPAP plus 2 plus, then you can simply do MPAP equals SPAP plus 2 times DPAP all over 3. So again, MPAP equals SPAP plus 2 times DPAP all over 3. In other words, the MPAP is 1/3 of the way from the diastolic pressure to the systolic pulmonary artery pressure. So these are all the different ways to calculate pulmonary artery pressures. Among the mean PA pressure, the first way and the second way that I showed you, I think are most useful. I don't really know of people who do it the third or fourth way. The fifth way can be valuable if you already have PA diastolic pressure and a PA systolic pressure. But try to remember the first way. So that's a wrap on systolic PA pressure, diastolic PA pressure, and mean PA pressure calculation.
This podcast is intended for qualified healthcare professionals and is designed for training purposes only. These materials should not be used for direct patient care or as a substitute for independent clinical judgment. For more educational content or to submit suggestions, visit www.rehu.com/meded.